This is section 5.1, the natural logarithmic function, differentiation. So we know that the general power rule works as long as we have a power on x that is not -1. We know that the antiderivative is raise the power by 1 and divide by the new power. And of course we can't let n be -1 because that would be division by 0. So what we are trying to find out today is, well, what if n is -1? What are we going to do? Well, we will not use the general power rule. Let me say that up front. This is not what we'll do if it's x to the -1, which is the same thing as 1 over x. So what we're going to be finding out today is if the function is x to the negative first, which is 1 over x, how do we integrate it? So we're going to use the second fundamental theorem of calculus to define a function that we will be able to use to get the antiderivative. Now, what we're going to be getting is not going to be an algebraic answer, nor is it trigonometric. And in fact, it falls into a class of functions called logarithmic functions, which I know you encountered in prior courses. As it turns out, what we're going to end up saying is that the natural log of x is defined to be an integral from 1 to x of 1 over t dt, provided that x is positive. And of course, that's because you can only take the natural logarithm of positive numbers. The domain of natural logarithmic function is x greater than 0. So if we want to interpret this geometrically, graphically, if we were to graph the function y equals 1 over t for positive t values, it will look something like that. And let's say that 1 is right here. So 1 over 1 is 1. And this is y equals 1 over t. So remember that we can think of the definite integral as an accumulation function. So if we start at 1 and go to some changing endpoint like x out there to the right someplace, the natural logarithm of x will be this area. Okay, that's how we're going to define the natural logarithmic function. If, however, we have a number, and that's for what we'll get when x is greater than 1, and I should probably say that since we're finding the area under a curve from 1 to x, that's going to be positive answers. Now, on the other hand, for x's that are positive but less than 1, if this is where x is, then when we find that integral, it's going to be a negative answer. And you can tell that because if we thought of the integral from x to 1 over t dt, as the area under that curve, the shaded area in green, but then wanted that to be an integral that starts at 1, we can switch the upper and lower bound using a property of integrals and switch those as long as we put a negative in front. Oops, that should have been a t. dt. And so because of that, that means that this integral from 1 to x that we'll actually be finding, if we multiply both sides by a -1, it will be a negative integral. because the integral from x to 1 going from left to right is positive, and then putting that negative sign in front of it, that negative sign in front of it means that any answer where x is less than 1 but still positive, the natural logarithm of that number will be negative. You can test that out pretty easily. Just go to your calculator and type in the natural logarithm of some number between 0 and 1, like 0.3, and see what you get. Type that in my calculator so I know what that answer is. Oops. About negative 1.2. 0.4. And if you take the natural logarithm of a number bigger than 1, like 7, you should get a positive number. 1.946 about. So obviously this is a positive answer and that was a negative answer. All right, so now that we've established that, how we get the natural logarithmic function, we can think about natural log of x and figuring out how to graph it. And since we have the, we can start with the differential equation dy dx is 1 over x. That means that the slope field that we could create would be, I hope I could put this picture in there, is I'm going to draw a field of things that have the correct slope. So when x is kind of tiny, 1 over tiny is kind of big, so these slopes will be really steep because it's a big number for the slope. And then as x gets bigger, like if you started with 1 over 10, I'm sorry, 1 over 0.1 is 10. And then if you went to 0.5, 1 over 0.5 is 2. And so that slope is a little bit smaller, but still positive. And when you got to 1, the slope of that would be 1. So that's a little bit smaller slope. And I'm drawing in little tangent lines because I don't know exactly where it's going to be yet. And then if I went to 2, 1 over 2 would be 1/2, which is even a smaller slope. I'll try to make those look like they have a smaller slope. And then 1 over 8 would be 1/8, which is, even a smaller slope. And if we were to draw a curve through this, one thing that we would want to know to do this graph is that the integral, let me start differently. The natural log of 1 is an answer we can get because of a property we've already talked about, because that's going to be from 1 to x, which is 1 in this problem. And whatever the function is, if the definite integral from any number to itself, so from 1 to 1, is always 0. So that means when x is 1, y is 0. So right here where, I think this is where I said 1 had a slope of 1, that's going to have a y value of 0 for the curve natural log of x. So what I'm trying to graph here, let me write this in red, we're trying to graph y equals ln of x. So if we follow the slope field, over here it's going to be a very steep curve, and then the slopes are getting smaller and smaller and smaller for the tangent lines. And so that's the curve and the way it looks. And of course the y-axis is a vertical asymptote for that curve. Okay, so that can justify for us what the graph of ln of x is that you probably encountered in an algebra class prior to this. It's kind of from a calculus perspective. So some of the things that you should know about the natural logarithmic function include, this is theorem 5.1 if you're looking at the notes, the domain is 0 to infinity, which makes sense when you look at the graph because we're only graphing positive numbers for x. The range is all real numbers. So it goes down on the left side forever, and on the right side it goes up and up and up forever, so that we end up using all real numbers for y. So that's the range. The function is continuous, increasing, and one-to-one, which means it's invertible. That's really important, that one-to-one. It means that we don't have to do any domain restrictions to get its inverse. It's invertible as is. And the graph is concave downward. So, a few properties that you should know from maybe paying attention just now and or algebra class earlier. We know that the natural log of 1 is 0. We know that the natural logarithm of a product is the sum of the natural logarithms of the factors of that product. The natural logarithm of a power is a product of the exponent on that power multiplied by the natural logarithm of the base of that power, so n times ln of a. And then the fourth one is the natural logarithm of a quotient, a over b, is the natural logarithm of the numerator minus the natural logarithm of the denominator. So a few properties that you should still know from your college algebra experience. Those are still true. So a few examples. These are not going to be that hard. They're just making sure that you can still do these college algebra level type things. The natural logarithm of 10/9, according to number 4, will be the natural logarithm of 10 minus natural logarithm of 9. That was A. B, the natural logarithm of the square root of 3x plus 2. And kind of in the same theme as derivatives and antiderivatives, anytime you have a radical, please feel free to rewrite it as an exponent. For a lot of the things we do, that's actually sort of required. So that's going to be 3x plus 2 to the 1/2 that we're taking the natural logarithm of. Then that 1/2 can come down in front, and we're going to have the product of that number 1/2 times the natural logarithm of the base of the power, the 3x plus 2. C, natural logarithm of 6x over 5 is the natural logarithm of 6x minus the natural logarithm of 5. And then, of course, 6 times x is a product. So that can be further simplified simplified. Expanded is another term that's used with this. This is the expansion of the logarithm using those properties up above, those 4. This is the expanded answer for C. And the compact answer is the answer in terms of a single logarithm. That might ring a bell for what the directions may have been for you in a college algebra setting. And please keep in mind these properties work backwards and forwards, so you should be prepared to use them in either direction. And so let's try another one. The natural logarithm of x squared plus 3, quantity squared, divided by x times the cube root of x squared plus 1. Since that's a quotient, it's going to be the natural logarithm of first the numerator minus the natural logarithm of the denominator, which is a product. And because of that radical being in the problem, I'm going to go ahead and take the opportunity to rewrite that as a power. Since it's a cube root, that's to the 1/3. Okay, so that 2 comes down in front of the natural logarithm, leaving 2 natural log of x squared plus 3. Anytime you write subtraction, you got to be very, very super aware of the fact that if what comes behind it is longer than one term, you should write a left parenthesis to protect that the subtraction affects everything behind it, for that term anyway. So I'm going to write a parenthesis here. And then this is natural logarithm of a product, so that will be natural logarithm of one factor plus the natural logarithm of the other factor. Okay, so the very first term is done, so I'm just rewriting that part of it. Just carry that along. Now I'm going to distribute the negative. I'm going to distribute the negative, and I'm going to go ahead and use that natural logarithm of a power rule to bring that 1/3 down in front. So I actually did two things here. Distribute the negative and bring the 1/3 down in front. And there you go. That is the expanded form of that original logarithm. So we have to be careful when we're rewriting logarithmic functions because the domain might change. For example, if you look at the natural logarithm of x squared, that graph looks something like this, because you can square any negative and get an answer. You'll actually have values over here. You still can't take the natural logarithm of 0. And you'll square x and get a positive answer, take its natural log, and you'll get that. By the way, that graph is supposed to be symmetric with respect to the y-axis. I just didn't do a perfect job of graphing it. So that's y equals. Now, if we were, however, to use that property, that should be the same thing as 2 natural log of x. And that graph is just the natural logarithmic graph we had before, multiplied by 2. So it just, still basically looks like that. Those two have a different domain. This is the domain is all real numbers except for 0. Whereas the domain for the second one is only positive numbers allowed. And so by taking that 2 down in front, we've changed the domain of what we can take the natural logarithm of. So you'll be governed by the original function and what you can do with that. So be very careful whenever you do these that you realize the domain might have changed. You may remember that when you first did logarithms in a in a college algebra type course, you had logarithm with various bases. The most common used in sciences is base 10, and of course our numbering system is based on base 10 because we have the ones place, the tens place, the 10 squareds place, the hundreds place, the thousands place, which is 10 cubed. So everything is base 10, and so that's a pretty common base logarithm to do. And we could have logs with various bases. Now, because of the definition we did up above, we in calculus like ln. It's the best logarithm for us. If you have a different base logarithm, it's going to be a little bit harder to deal with those, and so we're kind of hoping that doesn't occur much until we've gotten a little bit more experience. You may have known, for example, that whenever the base of the logarithm and the argument, or the number you're taking the logarithm of, match, then that answer is 1. It's a nice little fact that you might want to do. All right. So because we up above have a continuous one-to-one function, that means that it is invertible again. Let me just draw that same picture again. If we have the graph of 1 over t, that's the t-axis, that's the y-axis, this is y equals 1 over t, oops, 1 over t, then if we start at 1 and go to x, oh, sorry, let me change the color on that so you can see it better, and we go to x, we're finding that area. And so it seems reasonable that there should be some number x so that that area is equal to 1. Because of the continuity, we know that 1 has to be a value that we get because we're just accumulating that area. So x should exist such that ln of x is 1. And if we think about different bases, the natural logarithm is actually technically log base e. That's what the ln of x is. And everybody uses the ln of x notation. Nobody writes log base e. By the same token, people don't write the base 10, generally speaking, either. When you're talking about the common logarithm, it's just log of x, and that's assumed to be base 10. So there has to be an x such that ln of x is 1, and using the log base 10 of 10 equals 1 idea, it seems logical that that would be true if we were taking log base e of e. That should be 1. And so since log base e of something is ln of that something, it's 1. And so we have a transcendental number, e, kind of like pi. A transcendental number is an irrational number that cannot be written in terms of a radical. So it can't take like the 7th root of something that equals e or pi, except for like pi to the 7th. But besides that, there's no 7th root of an integer that would give you e or pi. You can't do that. So these are called transcendental numbers, and the value of e, as you might remember, is about 2.718. And if you look in the book or in the notes, it goes on further than that. I'm just writing those few decimals. 2.71828, 1828. You think, oh my gosh, it's repeating. It's not irrational. Actually, it is. Keep going. Then comes 46. So although you're kind of faked into thinking it's a repeating decimal, it is not. Like pi, the decimal representation of this goes on forever. And you should see e on your calculator, of course. You should be able to find that. On mine, it's second division sign, or if you want e to the x, it's second ln of, the ln button. Okay, so as it turns out then, the ln of e is, according to our definition of how we get ln, is going to be the integral from 1 to e, that specific value, 1 over t dt. And if you do that area from 1 to let that be e, then the area will be exactly 1. And there we have that. So, for example, if ever we have the ln of e to the nth, we can take that n down in front and then simplify ln of e as 1 and get an answer of n. And you can do that for a bunch of different values of x and get a bunch of different decimals. I think I put a table and a picture in there of this. So for various x values, what's the natural logarithm of that? And like when x is -3, you should get 0.050. When x is -2, you should get 0.135, etc. And then they show a graph of those points. So generally speaking, because of the transcendental nature of E, we'll be using our calculator when we want a decimal approximation of an answer. So just a little bit of practice for that. If you find natural logarithm of 2, since we're getting only approximations here, we'll write approximately equals. Type that in your calculator. You should get 0.693. B, if you type in natural log of 32, go ahead and do that. You should get about 3.466. And C, the natural logarithm of 0.1 is -2.303. Please remember that if the argument of the logarithm is bigger than 1, you expect positive answers. 2 and 32 are both bigger than 1, so we got positive answers. When you're taking the natural logarithm of a number between 0 and 1, like the third one, the answer should be negative. Okay? So that all should make sense. It's not self-contradictory, so that's good. All right, so if we then want to take the derivative of the natural logarithm of x, that's going to be the derivative of the antiderivative from 1 to x of 1 over t dt. And using the fundamental theorem of calculus, we know that we can do the derivative of an antiderivative of a definite integral from 1 to a variable, or from a constant to a variable, by just substituting that variable in for t, so 1 over x. And if that variable expression is more complicated than that, you'll need to use the chain rule and multiply this by the derivative of that upper bound. And the derivative of x is 1, so times 1 won't change anything. Okay? And keep in mind that although 1 over x itself can take on negative values, natural logarithm can't. So our restriction will be that this is only true for x's that are positive. And in a more general sense, the derivative with respect to x of the natural logarithm of u, where u is just some function of x, will be 1 over the argument of natural logarithm times the derivative of that inside function. So what I'll be saying is when you're taking the derivative of the natural log of something, the answer is 1 over that something times the derivative of that something. And that something can only be positive. Again, because the natural logarithm of a negative or 0 value has no meaning. Okay, so let's do a few examples. Here's A. What's the derivative of the natural logarithm of 2x? Well, that's going to be 1 over the something, 1 over the 2x, times the derivative of that something, so times 2, and that simplifies to be 1 over x. Now, interestingly enough, if we had rewritten natural log of 2x using one of the properties up above, that would have been natural log of 2 plus natural logarithm of x. And if we took the derivative of both sides, then the derivative of that would be the derivative of the constant natural log of 2 is 0, and the derivative of ln of x is 1 over x. And of course that simplifies to be the same thing we got before. So the good news is that those properties don't change. They're still valid, as shown in that last example. Okay, this time for b, we're taking the derivative of the natural logarithm of x squared plus 1. So the derivative is 1 over the something that the natural logarithm is taken of, 1 over that something times the derivative of that something. And so that's 2x over x squared plus 1. Okay, C, the derivative of a product like x natural log of x. Well, of course, this is a product rule that we're going to have to use first primarily, because we have a product of x times ln of x. So this will be the first function x times the derivative of the second function. The derivative of ln of x is 1 over x, plus the second function, ln of x, multiplied by the derivative of the first function, and the derivative of x is 1. And so this simplifies to be 1 plus ln of x. Okay. Then part D, we're supposed to find the derivative with respect to x of ln of x quantity cubed. So this is the derivative of a power. We have something cubed, so its derivative will be 3 times that something to the reduced by 1 power, so squared, times the derivative of the inside function, 1 over x. And so simplifying this one, I get 3 over x times the ln of x quantity squared. Okay, let's see what else we've got here. Oh, I want to throw in one more example that's not in your notes. So I wanted to do a quotient rule problem. So let's do the derivative of ln of x divided by x squared plus 1. This is a quotient, so the quotient rule applies. So low d high, the derivative of the numerator is 1 over x, low d high, minus high, so ln of x, d low, so times the derivative of the denominator, which is 2x, all over the square of low. Which is, see, x squared times 1 over x. I'm distributing the 1 over x. X squared times 1 over x is x, plus 1 over x times 1 is 1 over x. The best way to write that product is with the polynomial part in front and the ln of x behind. And then this is a complex fraction, that is a fraction that has a fraction in it. So I'm going to find the common denominator for all the little fractions in the problem. There's only 1 over x, and multiply by 1 in the form of the common denominator of all those little fractions over itself. And so that becomes, when you distribute, x squared plus 1, of course now the fraction's gone, minus 2x squared ln of x, it's an n, all over x times x squared plus 1 squared. All right, this is a good stopping point, so I'm going to halt this and go to another part for the rest of the lecture.